Hey everyone, welcome to Breaking the Rules, Dynamic Navigation in Modularized Apps. Also known as this talk may or may not solve all your navigation problems in 40 minutes, but we'll see. So this actually came about from my experience working in heavily modularized code bases and then trying to graft navigation components on top of that. Because both of those things, modularization and nav components, introduced scoping. And we all know scoping is great architecturally, but it makes things kind of tricky when you're trying to make navigation a bit more custom and a bit more dynamic. So we'll talk about some of those cases today. And also, I gave a simplified version of this talk last year, and a lot of the questions I got were, well, how do you do all of this? Nav components in a modularized app with Jetpack Compose. So today we'll talk about how to do all of this in a compose context as well as non-compose. If you don't know me, my name is Sumayyah Ahmed. I've been an Android engineer for 9 years. I've worked in both startups and large corporations, and occasionally I spend my time up on stage talking about nerdy Android stuff, one of which is navigation. But we'll start with a bit of context. So pretty much everything, and by everything I mean most things, is modularized these days. It's one of the hallmarks of a modern Android app. And when I say modularized, I mean anything from Gradle modules to independent libraries, just some way of partitioning your code into single responsibility units. Actually, can I get a show of hands? How many people are working in a code base that's at least partially modularized right now? That's pretty much everyone. I should have asked for people who aren't modularized. But we all know there's good reasons for this. I mean, apart from the obvious benefits to our build times, things are much more tightly scoped. So as single responsibility principle, everything related is in one place. Everything's encapsulated. So very tightly controlled points of access and points of change for code, which of course means you can control the points of failure. And your code becomes much more reusable. So we've modularized, everything is great. What could be better? I mean, if you were at the keynote, you know that you shouldn't all drink the Kool-Aid, but at this point, we know that modularization does come with complexities and downsides, one of which is navigation. So now that everything is much more closed off, how do we do navigation with nav components? What changes? The good news is not much necessarily. So if you're inside a modularized enclosure, say you're inside a Gradle module and you want to get from point A to point B, I mean, we are free to use intents if A and B are activities, or transactions if they are fragments. And of course, now we have the nav components library, so we can delegate all of that work away, take away all the manual labor that we used to do, and tell the controller to simply navigate with the ID of B. But there is a big assumption that we're making here. We're assuming that B is discoverable from A, that A and B exist in the same scope, which in nav components world means we're assuming A and B exist in the same navigation graph. That's what allows the controller to find B when you're in A. That's by design because nav components has now introduced scoping. So what used to be some random bits of code floating around in our fragments and activities is now navigation logic, which is its own entity. It's self-contained, independent entity responsible for its own internal logic and encapsulated. So we can't take it for granted anymore the way we used to in our monolithic apps, that every destination at compile time is accessible from anywhere else. Now, access to destinations is an issue. That's actually part of the design of nav components. It's meant to be heavily scoped and encapsulated. Typically, you would have your top-level components owned by something high up in your view hierarchy, typically your activity, because it's sort of assumed you have a single activity, multiple fragment architecture. And that's what owns your three major nav components. There's your host, which is your container for your views. There is your graph, which defines all the destinations you can get to. If it's not in your graph, you can't get there. And the last part is your controller, which is your handler between the code that we write and all the stuff that goes on inside nav components. It's going to be self-contained graph inside a self-contained activity inside a self-contained module. By the way, how does all of this change when we start dealing with Compose? Because a lot of the Vue stuff is in XML. What if we get rid of XML and switch over to Compose? What happens then? Actually, that's heavily dependent on how we choose to implement Compose, at what stage we're in the migration. I mean, navigation with Compose is itself a huge topic. But there's two major cases that will cover most people. Case number one is the interoperable approach to Compose, which I believe most people start with in any case. And this assumes that all of our architecture remains the same. Our activity fragment architecture, the way that we set up the navigation components is still the same. The only thing that really changes is that our fragments, instead of rendering traditional views, are now rendering composables. In which case, as you can see, navigation-wise, nothing really changes because your graph still defines the destinations you can get to. The internals of these destinations, how they choose to render their views, is completely unimportant for navigation purposes. It doesn't care. The second case can make things a little tricky. Now, let's say we get rid of fragments altogether, we get rid of XML altogether, we're in a 100% Compose world. As you can see, it doesn't change a lot. So your navigation host is still there, except instead of being inflated by your XML, it's probably going to be owned by a top-level composable in your activity. You still have a controller, except it's a nav host controller, not that different from a nav controller from a developer's point of view. And then your graph still defines all the destinations that are available to you, except they are now composables. So whether we use Compose or not, the fundamental problem remains the same. If we want to get from A to B, but A and B exist in different scopes, if they exist in different navigation graphs, how do we do that? How do they know about each other? The recommended way is to and of course this problem gets compounded when you deal with a modularized architecture, because let's say this is a pretty simple diagram of, say, 3 feature modules. Each of these are going to have their own activities with their own navigation graphs, and none of these graphs will know anything about each other. So how are we expected to navigate? Which brings me to the recommended way. The default assumption is that we are going to maintain encapsulation. We're going to work with all of this built-in scoping. So if we want to get from activity A to activity B, our activity architecture is assumed to be architecturally very similar to modules. These are self-contained activities which manage all of their own internal logic and all of their own internal navigation flows. So getting from A to B means A is going to launch B and then completely relinquish control and knowledge of what happens next. Activity B inflates, it's going to start inflating its own navigation graph, it takes over its own internal logic. It's basically a handoff process. This is the kind of navigation I refer to as static. So everything is known at compile time, all possible paths and destinations are defined, and that is not real life. Because leaving aside the fact that none of us have architecturally perfect apps, this doesn't even take into account the fact that we will very likely have to deal with unknowns. It's extremely possible that sometimes you just don't know where to go next, where to navigate to next, until some code executes at runtime. What if you want to customize your navigation paths for user type or lines of business? What if you want your navigation experience to be different based on the path you took to get there? So say you have a fragment C, you want that experience to be different based on whether you got there via A to B to C versus D to E to C. How are we going to remember our navigation path? All of this is what I think of as dynamic navigation. Now we're putting together these experiences that change at runtime based on what the user has been doing. It's very common, and let's break the rules a little bit to see how we can do it. So to make this more manageable, I'm going to go through 3 specific case studies with code, and we'll also do a deep dive into nav components as well, because once we understand how nav components actually works, breaking the rules gets easier and we can do more of it. let's start with case number 1, which is something I've actually encountered more than a few times. We want to get from activity A to activity B, but we don't want to hand off. We want a particular point in activity B's navigation graph. We want fragment B, for example. But the developer knows about fragment B, but activity A's graph knows nothing about the internals of activity B's graph. They're still encapsulated. So how do we make this happen? We're actually just talking about implicit deep links. And nav components does support this. We actually are able to build deep links, and that lets us create these very specific paths between navigation graphs. While maintaining encapsulation, we're not going to break those rules necessarily. Also, as a bonus, this type of deep linking works if these graphs belong to completely different modules. So let's see how we can do this. Let's look at code, and it's going to be a 3-step process. Step 1 is to make our destination deep linkable. So however we've defined this destination, here it's the traditional XML. This is our fragment B we want to deep link to. We can do that by assigning a deep link attribute. The same way that we assign an action or arguments attribute, we assign a deep link attribute. And the only thing that's really important here is assigning a unique URI. So that's step 1 on the destination side. Let's go to step 2, which is on the caller or the source side. Or in fact, there's a step 1.5. If these graphs are in different modules, make sure there's a compile time dependency so they know about each other. And then our source graph needs to reference the destination somehow because, of course, if it's not in your graph, you can't get there. So we need a reference to our deep link destination. But we can't do this. This is not valid because fragment B still belongs to a different graph. So even though these graphs have compile time access to each other, it doesn't mean they have access to each other's contents. What we can do is nest the destination graph inside the source graph. We'll talk about why this works in a second. And also, by the way, nesting graphs is totally okay to do. It's actually great for reusing logic and navigation flows. And it means that our navigation flows can be broken down into smaller, nicer, single responsibility chunks. But I digress. Nesting graphs is necessary for deep linking. So that's step 1 and 2. The last step is the part that executes at runtime, and that is to actually perform the deep link. And that's very similar to the way we navigate with IDs. We just navigate with a parameter, except in this case, it's a nav deep link request, essentially a wrapper around the unique URI that we created. And this simple process actually ensures that your graphs will create this path between them, that you will deep link to fragment B, and only fragment B will be added to the backstack. How will this change once we start using Compose? Well, again, that depends, but we have 2 cases that we can deal with, so let's take a look at those. Case 1 was the interoperable case, and remember, this is when nothing changes except for the views. So activity fragment architecture is the same, our nav components are the same, our fragments are now simply hosting composables, or in fact, even a mix of composables and traditional views. In which case, deep linking remains the same. The work we have to do is a lot less. Hooray! Because if you look at this code and you think, what if fragment B has composables in it? Doesn't matter. The way that we create our components is the same. The way that we define our graphs, the way that we perform the nesting is the same. And the runtime execution code doesn't matter. Compose is going to sit at a different layer from this type of navigation logic. This is going to change, though, when we start working with 100% composables. Because at this point, now there's no more XML, now there are no more fragments, and our views are composables. How on earth do we perform deep linking in this case? Well, as we said before, it's not that bad because our top-level composables are still there. There's still a graph, and it does the same thing. It's just all going to be programmatic. So let's take a step back and think about how we would typically set up components like this. So again, multiple ways of doing this, but it's recommended to have them available somewhere very high up in the hierarchy, typically in your activity. So let's say our activity is going to call a function called composable function called setupNav in our onCreate cycle. And as you can see, we've got our controller element, we've got our navigation host with a reference to the controller and the graph. And if you're wondering where the graph is, it's declared implicitly here. And as you can see, we've got a couple of composable destinations. So now that everything has been set up, let's start constructing our deep link. And it's going to be the same three-step process. Step one, we make our destination composable, deep linkable. So as you can see, I've defined this graph called graph2 with 3 composable destinations, nested screens 1, 2, and 3. The third one is the one we want. So we assign it a deep link attribute, and we make sure there's a URI defined. Over on the source side, however we've defined this graph, we've got a couple of composable destinations, and we make sure we nest graph 2 inside the source graph. Third step is pretty much exactly the same as what we did before. We wrap the URI in a nav deep link request, and we pass it as a parameter to our controller. So whether we're using Compose or not, as you can see, the fundamentals of navigation remain the same. The way that we construct our requests, the way that we construct our navigation logic is going to be very similar, even though as we know, there's some syntactic differences between the two. Speaking of navigation, how does this even work? So how is navigation not breaking its own rules here? Because we're still going to maintain encapsulation in these graphs, but somehow we're still constructing this deep link, and we're allowing it to pull fragment B, and only fragment B specifically, to put on the backstack, without bringing the whole internal, like start, destination, et cetera, from the destination graph. The answer to that is actually in how nav components works behind the scenes. So let's talk about that. The very first thing actually happens at inflation time, way before we even start doing any navigation. That's when your activity goes into its onCreate cycle and starts inflating your top-level nav components. One of the important things that happens is that there's a class called nav_inflator, and it finds our destinations however we've defined them, programmatically or via resources or whatever type they are. In our example, we're going to take a couple of fragments and a nested nav graph. So nav_inflator finds these and wraps them in another class called, surprise, nav_destination. And all of these nav destinations are added to an array belonging to the nav graph instance. And of course, our controller instance is going to have a handle on your graph and a backstack via the activity. This allows the controller to not care about type-specific stuff. It doesn't care about fragments or activities or composables or whatever is in the destination, what parameters it needs. It cares about finding the right destination. So where exactly is navigation happening? Well, that control is actually pushed down to the nav destination itself. Once the inflator is done with it, each instance is going to look something like this. There's some properties that we gave it, like the class type, actions, arguments, deep links, and this class called a navigator. It's going to be a type-specific extension on the abstract navigator class, and this is the class that actually executes. So your fragment navigator is going to use transactions, your activity navigator is going to use intents. All the code that we used to write and manage is now the responsibility of the navigator class. And this makes it really cool because now your controller delegates the control down to each destination itself. Every destination knows how to put itself on the backstack, depending on what it is and what it needs. Your controller is just going to flag it, and then it executes itself. So what happens when we run this line of code? The first thing is that your controller is going to extract that unique identifier, which is usually the ID, but in this case, it's the URI that we defined, and pass it to the nav graph to say, find the matching destination. And in our example, the nav graph is going to take the URI. It's going to try and match it against fragment A and fail, fragment B and also fail. And then we hit that nested nav graph. Now, this has also been through the inflation process. So behind the scenes, it's going to have its own internal array of nav destinations, one of which is the match that we care about. So again, it takes the URI and matches it against number 1, fail, number 2 is a fail, number 3 is a match, and because that, of course, has its own navigator, it knows how to execute itself and put fragment B on the backstack. Note that the inner graph didn't need to share any context or information or data with the outer graph. Control is pushed in one direction, and that is downwards. Your controller gives the power of execution down to any destination that flags itself as a match. And this works for nested graphs because the nested graph is able to apply that control to its own internal array. And that's what allows deep links to work without breaking encapsulation rules. Now I'm going to start contradicting myself. I've said a couple of times that if a destination isn't in the graph, you can't get there. That's not strictly true. Destinations have to be in the graph by runtime to let you do navigation. That doesn't mean that everything has to be there at compile time. Somewhere in between the two, we have the power to mutate our graphs, and that lets us do navigation more dynamically on the fly. Let's see how this would work. What if you don't know where to go till runtime? Let's say that you have a contract with some external module to provide content for you. And if this sounds weird, it actually happened to me. Something like, let's say we're in a navigation graph. We're in fragment B, and we know some callback is going to execute. Our module is going to provide a fragment for us to render as our next step. Well, it doesn't belong in our graph, so we can't get there. We can't deep link to it because we have no control over this external module. What do? Luckily for us, we can modify graphs on the fly. Nav components lets us add and remove destinations as we go. So let's see how this can solve our problem. We're in fragment B, this callback executes, we've got a destination fragment class. That's great, but our nav controller doesn't care about this fragment. It cares about destinations. So let's make one. There is actually a create destination function exposed by the navigator provider. So we can create one, pass it some important information like the ID and a label, and of course the type of fragment it needs to wrap. And then we place it in our graph. And that makes it findable and navigable from everywhere else in the graph as if it was always there. And now, of course, the last step is just to navigate with the ID that we defined earlier. We're taking advantage of the fact that, again, the controller doesn't really care that this fragment D came from somewhere else, that it doesn't belong to this module, or the fact that we just created this nav destination 1 second ago. It just cares about, at the point where I do navigation, does this destination exist in this scope, in this graph? If so, I can get there. And this is really dynamic navigation. We're stitching together navigation logic on the fly based on what the user has been doing. And in fact, there's a lot more that we can do now that we know our graphs are mutable. We don't need to predefine everything. The graph that we have at compile time isn't the graph that we're going to end up with at runtime, and that's totally fine. We don't have a lot of time to go into this, but this is an example of code from the Android documentation page on Kotlin DSL. And now it's possible to create navigation via configuration. So we define a nav configuration in our DSL, we can share it, import it, export it, and build a graph around it programmatically. In fact, we don't even need to have a graph defined at all, except perhaps the start destination. We can start with completely skeleton graph and flesh it out as we go. And even, let's say that every experience at runtime results in a different graph, doesn't matter, we can still create it. So there's a lot of stuff we can do with this, and it's very exciting, but there's one last piece of this, and that's data sharing, which we haven't talked about yet. When you have all of these destinations from different sources sharing the backstack, and by default, it is the shared application backstack, how are they going to communicate? Why should they? Well, take a case like this. This is your backstack, you are in fragment B, and then there's a deep linked fragment on top. What if your fragment B needs to know what happens in this deep linked fragment? They don't share a view model, or activity, or a navigation graph, or probably not even a data store. How are they going to communicate? The only thing they have in common is the backstack. And that's what we're asking. How do we share data across backstacks? Nav Components actually prefers that we use nav graph view models for this, which is pretty much exactly what it sounds like. It's a view model scoped to a navigation graph, and it's available to all of the destinations within our graph. But does this help us? Remember that fragment B and this deep linked fragment still belong to different navigation graphs. So their nav graph view model objects will reference completely different things. This one doesn't work. What can work is save state handle. And if you're not familiar with this, it's part of the Android Jetpack library. It's basically a souped up saved instance state. It's a data store that allows you to read and write key value pairs, which is guaranteed to survive process death. And nav components lets you access it in a really interesting way. So here's your nav controller. It has a handle on the backstack. In fact, it can be multiple backstacks, but let's keep it simple. Every time a nav destination is added to the stack, it's wrapped in another class called nav backstack entry, and which is an extension on the old backstack entry class. And that just gives your destination some extra stuff. So in addition to the destination itself, you have this thing on the top. See the saved state registry? That's your data store. And that's available for reads and writes as long as this destination is on the stack. Part number 2, not only that, but your controller exposes public functions to let you access entries on the stack. So if you have access to a nav controller, you have access to other entries on the stack, along with their properties, including their save state handles. As an example, let's see how this works in code. Fragment B is in the foreground, and it needs to know something high level about what happens after it. Let's say it needs to know, has the user seen some new onboarding flow? It can ask the controller to access the current entry, which is itself, and use its save state handle to set some flag to false. Let's call it has seen new flow. Now, let's say we perform a deep link from another external module. That's the new onboarding experience. The user has seen it. We're good. It can ask its nav controller. Remember, different nav controllers can still reference the same backstack. It can ask its nav controller to get the previous entry, which is fragment B's entry, get its saved state handle, and set that flag to true. And then it pops itself off the stack. Once fragment B comes back to the foreground, it can read the latest value of this variable and react to it. What we're doing here is we're building a memory of where the user has been and what they've been doing, even when these destinations don't exist anymore. Save state handle allows us to store this type of transient session-based navigation data that you really can't store anywhere else. And of course, this was a simple example, but there's a lot more that we can do with this. Save state handle becomes more useful once you start working with composables. Actually, the backstack entry itself is a lifecycle owner, so we can set observables on it via live data and react to any changes in the entries dynamically. So again, a lot of stuff we can do with this. But I've been talking for a while, and I want to wrap up with 3 main points. The first is that the fundamentals of Android navigation haven't really changed. Behind the scenes, we're still using the backstack, we're still using intents and intent flags and tasks and multiple backstacks the same way that we've been doing for years. So thank God, we don't need to relearn a lot of our fundamentals. What has changed is access and responsibilities. Now there's a whole layer of abstraction on top of this in the form of navigation components. And although it's really powerful and it simplifies a lot of stuff for us, that's an added complexity, especially when we're dealing with architectural complexity on top. So understanding nav components is really the key to unlocking a lot of the more fun, dynamic stuff that we can do, and a lot of the real-world situations that are going to happen to us. The good news, again, is that Compose doesn't change a whole lot. So Compose, to me, sits somewhere like 1 layer below navigation in the Android architecture layer cake. It's primarily concerned with the rendering of UI and UI views, or view state. The actual swapping out of these views, the navigation logic, is somewhat different. So even though there's some syntactic differences between Compose and non-Compose, there's quite a lot of interoperability built in because navigation isn't concerned with UI as much. It's going to work fundamentally the same way, the same classes doing the same things. So thank you so much for attending this talk. I had a lot of fun digging into these libraries to figure out all of this. And we have about 5 minutes for questions, so feel free to just shout it out or come up to me, and I'll do my best. Thank you.
Okay.